So the steady state response of resistance, inductance, capacitive elements to sinusoidal excitation. What does it mean? Is that previously we have the network which consists of usually all kind of elements active and passive. Let us consider if the network has resistor or inductor which is L and capacitor which is C, and if these are connected with a source, what kind of source is that? Sinusoidal source. Now the source representation is like sine symbol as like this. So it is the sinusoidal source. So the source will look like, for example, V of t is equal to Vm sine omega t plus theta form. This kind of thing. If it is a current source, we may see this as Im sine omega t plus theta form. So in either of these kind of sources are connected for a network which consists of resistor, inductor and capacitor. So in order to understand the combined response when the circuit consists all these kind of passive elements, we should understand first what is the basic property of the resistor when it is excited with sinusoidal. What is the property of the inductor when it is excited with sinusoidal? Similarly, for capacitor. Once we see resistor, inductor, capacitor behavior individually, then we can take up resistance and inductance combination, resistance and capacitance combination, and we can make all the combination like resistance, inductance and capacitance. So if we know individual behavior, it is easy to study the combination behavior. So that's why let us see the steady state. You should understand this steady state meaning also, that steady state, steady state, steady state means, just let me give you a generalized thing that, so whenever, whether you observe at your home or not, let us assume that you have power supply in your home. Just you are closing the switch, at some instant, let us say t is equal to 0. In this closing operation, let us assume that you might be switching on a motor to pump the water into your building overhead tank. If that motor is a little higher rated, then could you observe some blinking in the tube light brightness? Anybody observed that? There will be certain blinking nature when you switch it on or switch it off. Then after some time, after like 1 second or 2 seconds, that brightness remains constant. That means the moment when you switch it on or off, there will be sudden variations in the voltage and current. Due to that, the brightness of the lamp going to change continuously. But after certain time, after we leave certain time, then it will remain certain constant brightness. That constant brightness at which the lamp is producing, we call as a steady state. Steady state. So this you can see just a simple generalized example that, so for example, so uh, let us say you are going to appear one exam. So one exam. So one very important exam for your career. What happens is that the moment you enter into examination hall, for like first to 10 minutes you will feel little tensed. Let us say 0 to 10 minutes you will feel little tense. Why? Because this is so important and how you will perform, that you will have little tension in you. But after some time that becomes habituation and you will get aware of the exam hall and invigilator and all other side by persons, everybody, and your mindset will reach to certain value, certain position, that now no more fear, no more such things, just simply you will be performing at constant level your examination. So this initial duration we call as transient situation. Transient situation. Transient means a sudden change. Like previously, you haven't entered into the exam hall, and just suddenly you entered into exam hall environment, which is creating your brain to be a different environment suddenly. But after certain time, depends on the person to person. One person may get quickly adapt with that environment within 5 minutes or within 1 minute, and one person may take 10 minutes of time. It doesn't matter. Certain duration of time will be there for every person to reach to certain normal state. That normal state we are calling as a steady state, where you will not have any sudden variations in your behavior. So that we call as a steady state. That means now we are not studying any transient state behavior. Just we are switching on this supply, which is of sinusoidal in nature, and we wait some time. Then it reaches to the normal state, which we call as a steady state. Then we analyze what will be the voltage across the resistor, what will be the voltage across the inductor, etc. That kind of study we call as a steady state analysis. Remember that steady state analysis does not have any sudden variations. Okay, right. Now let us see element by element. Let us take the response of first element, that is what, the response of resistance or pure resistance. Let me take pure resistance. One should understand what is meant by the response. Response means output. So now let me take a resistor, and resistor has two terminals whose value is R. Let us consider a voltage of V of t is applied for this. As a result, a current of I of t is flowing through the resistor. If we consider this applied voltage is V of t is equal to Vm sin omega t, you can consider cos omega t also, no issue. Vm sin omega t. Now let us try to see all the parameters when we give this kind of voltage for the resistor. So first what I will do is that whenever we deal with this sinusoidal response, preferably I will try to put this given voltage or current into phasor form. Simply I will use same notation, but here try to observe this is small case letter V, whereas this is capital letter V. On top of it I will use bar. What does it represent? Phasor form of this voltage V. What is that value? I will write, instead of writing every time Vm by root 2, simply I will say V at an angle 0 degree. Why? See this? It look like Vm sin omega t plus 0. So I am taking magnitude where V is equal to Vm by root 2. Where this V we call as RMS value of the voltage. This is called as a RMS value. I told you that you can express this in Vm or we can express in RMS value. If it is RMS value, we specifically call this as a phasor. If it is a peak value, we call as a vector. Okay. Right. So now I have voltage and I have resistance. Can I find the current? So it is simple thing that the current is equal to, according to Ohm's law, voltage divided by resistance. A simple law. How much is the voltage? V at an angle 0. How much is the resistance? R. This resistance is a real number. Means real number like 10 can also be written as 10 at an angle 0. Or it can also be written as 10 plus j into 0. All are same. Okay. Simple real number can be written as 10 at an angle 0 or 10 plus j0 in polar form or rectangle form. If it is so, what we get here? V by R at an angle 0. And this V by R, I can consider current I, current magnitude, where I is equal to voltage magnitude divided by resistance. Try to observe, voltage magnitude is different, voltage phasor is different. That you need to observe carefully. V bar means phasor, V means only magnitude. Okay. So if you want, you can make in some more different ways like this. V is equal to mod of V bar. If you want, you can make a note of this. Means magnitude of V bar is what the V. So I got the current, I got the voltage. Now, can we plot these two things onto some phasor diagram? This is also very important. All of you concentrate carefully. Whenever you want to draw the phasor diagram, preferably take this coordinate system like, so this I will call as alpha axis, this I will call as beta axis, like x and y axis. Alpha axis represents 0 degree position, which we call most of the times as reference axis. Reference axis. Now, as you move in counterclockwise direction, you will gain the angles. Those angles are referred as positive angles. If you move in clockwise direction from the reference axis, those are referred as negative angle direction. Negative angles. That means from here, if I move by 90 degrees, I will reach to the beta axis. So beta axis can be represented as simply 90 degree, or it can also be equivalently represented as J. Further, if I move from the beta axis, then if I travel some more angle which is 90 degrees further, altogether it becomes 180 degrees. So this 180 degrees can also be named as, here I traveled one more J. So here already J traveling happened. So J and J, so it becomes J square, which is equal to minus 1. Minus 1, which is negative alpha axis. If I will take one more 90 degree from the 180 degrees position, it becomes J square into J. Each 90 degrees is corresponding to a shift of J. J is equivalent to 1 at an angle 90. J magnitude is 1. Angle contributed by J is 90 degrees. So J cube, so how much we will get? This is minus J. So this altogether angle is 270, or if you come back in this way, this can also be equivalently said as minus 90 degrees. I will show how it is minus 90. Minus 90 degrees. If I travel further, one more J corresponding thing. So J cube into J power 4, that is J power 4 is equal to 0 degree. Means we reached to 360 degrees position, which is equal to 0. 1J, let me write here, 1J is equal to 1 at an angle of 90. Okay. So J square is equal to minus 1 j cube is equal to minus j and so on j4 etc. j power 4 etc. This is in counterclockwise direction. If I travel in clockwise direction, those becomes minus j into minus j like that. Okay. So right now let us see what will be the voltage and current of these resistor. So let me take once again here resistor. This is R whose voltage is, see carefully how I am representing, V bar, whose voltage is V bar, whose current is, tell me, I bar. Now let us put these things on alpha beta axis. This is alpha axis, this is beta axis. Now see that what will be the voltage? How much is the magnitude? V. What is the angle? 0 degree. Where is the 0 degree position? Reference position. So I should lay one line on the alpha axis whose length is equal to V, whose length is equal to V from the origin, and just indicate one arrow for that. It represents phasor, where this length of the vector V lying on the alpha axis. What is alpha axis represents? 0 degree. 0 degree. Of course, it is reference. Next, what about the current? Check the current. How much is the current? Current magnitude is I. Current angle is also 0 degree. That means this current phasor also should lie on the same line of the alpha axis as like this. But this may have lesser length or more length depends on the value of the R. This is what I. So these two things like representation of voltage and current on these alpha beta axis we call as phasor representation or phasor diagram. We can call this as a phasor diagram. Phasor diagram, which representing phasors of voltage and current of the resistor. Voltage and current of the resistor. Now try to observe here very important feature that the voltage, let me write, the voltage is in red color, voltage V bar and the current I bar are in the same line and which are coinciding with each other. So that nature we call as voltage and current are in phase. In phase in the sense that the phase angle of voltage and phase angle of current are same, which we can say that phase difference between them is 0. In phase means 0 degree. Clear? In phase means 0 degree. So just you can say this in phase can also be said as angle difference of the phasor of the voltage minus angle difference of the phasor current is equal to 0. Means phase difference. This we call as phase difference. So how much is the difference from voltage vector, this line, arrow line, to the current line is 0. That is what we call or in phase. This terminology is very important. Very frequently I use this. In phase. In phase means phase angular difference from that corresponding voltage to current. This is the difference. Is 0. Clear? Right. So with this we can also proceed in finding some more additional thing which is important, that the power. So now just see that, so we can proceed in many ways that, so as because we already have phasor V is equal to V at an angle 0, I is equal to I at an angle 0. So from this, can I transform back to the voltage V of t as V into root 2 at an, this is sine function, right? Which function I chosen initially? Sine function. How much is the angular frequency? Omega t. So get back that sine function here. Sine omega t plus 0, and whereas for current also I can get I of t is equal to I into root 2 sine omega t plus 0. Now try to get the power P of t, instantaneous power. P of t is equal to product of voltage into current. Product of voltage into current. So I'll do in phasor form. You try in the generalized time domain form as like this. V into root 2 sine omega t into I into root 2 sine omega t. You simplify this and get the P of t, then take average of that. How we get the average? 1 by t integral over 0 to t P of t dt, and see that how much power you will get. And how much power we will get, that we can do in the phasor form as like this. So P average directly I am writing, just cross verify whether you will get the same value or not. P average is equal to Vi cos 0. What is this 0 is? Angle difference between voltage and current. This 0 degree. 0 degree. So cos 0 is 1, so I will get this as Vi. Simply P average I will get as Vi. Cross verify whether you will get P average as Vi or not. Okay. So like this we can proceed in checking the voltage, current, power for every element. And just quickly let me show for the inductor also. So let me write the response of inductor. Response of inductor and quickly show me the inductor symbol, and let us assume that this inductor is connected with a voltage of V of t. As a result, it is circulating a current of I of t. So if the inductance value is L, so you can assume either voltage or current here. So let I am considering the current for easy simplification as like this. I am sine omega t. Then the moment you will consider the current in time function, just quickly go to phasor representation as I at an angle of 0. Then if you want, you can get here itself how much is the voltage. Voltage across the inductor is proportional to the rate of change of the current. That is L into di of t by dt. And see that how much we will get? L into so I am sine omega t. So d by dt of I am sine omega t. So how much is the differentiation of sine? L into Im cos omega t. Clear? Is there any other term? Omega. So now try to see this. I can make omega into L Im cos omega t. This is what the voltage. But if I want to compare this voltage and current, I need to convert one into other form. Definitely both must be either in sine form or cosine form. And if you want, preferably you can convert into cosine form. So as because we already assumed this current, you can convert this cos into sine also, nothing wrong in that. And just we are having only comparison between these two. Then how can we do that? Just see that. So let me take again this table, yesterday what we had seen. This is the sine minus sine, cos minus cos. Now what is my desirable is here as of now, I want to convert this cos into sine so that I can have voltage and current both are in sine, I can compare it. Okay. So I need, this is what the desirable. Sine is my desirable. From where? From cos. Then what do I need to do? See, if I am moving in clockwise direction, that represents negative angle. If I will move by 90 degrees, I will be reaching the sine. So now I can say that this is equivalent to this omega L into Im, omega L into Im, uh, right? Yes. It is desirable to this, so let me write in another way. So as like this, I need the sine function. So from sine, if I travel plus 90, then I will be getting cos. So I can write this cos equivalently as sine of 90 plus this function. So sine of omega t plus 90, sine of omega t plus 90. So this you can further simplify and just to see that voltage can be represented in this way. Omega L one term, let me keep as it is. I want to write this as, or for example, let me write in phasor form, then I will come back again. So V bar is equal to omega L Im at an angle of 90. See that? Now V and current both are in sine function. So no issue. Both should be either in sine or cosine. This is a sine, this is also in sine. So now just I want to make small change here, that I will write this as omega L at an angle 90 into 1, that means Im at an angle 0. This further I will write as omega L at an angle 90. Just let me bring this little this side. Im, or let me, yeah. So in the next step directly I can make this as two things. V bar to the time function V of t. How can I write is 1 at an angle 90 is equal to j. So I will write j omega L. This Im at an angle 0 is equivalent to I of t in time domain. So I will write as I of t. I hope you got this point clear. From the phasor to time function. So 1 at an angle 90 is equal to J. So into omega L is this thing. Now try to see voltage to current ratio. This is why I expressed this into again sine form and again convert back into current. Just I want to take the ratio, I want to see the comparison. What is the voltage to current ratio generally? Resistance. But in case of AC, we will not have resistance. In its equivalence, we will have impedance. What is that impedance? Is J omega L. This will have the units of the ohms. So this can also be represented as J into XL, where XL is referred as inductive reactance, inductive reactance, which is equal to omega L. And now we can make conclusion that for a inductor, if we give a sinusoidal excitation with angular frequency omega L, its equivalent AC representation will become JXL or simply J omega L. And whose current is I, whose voltage is V. Now based on this you can explore some more points out of this as like in the phasor diagram. So now you can see that what is V bar and what is I bar. I bar is equal to I at an angle 0, that what we got. How much is the V bar? V bar I can consider this entire thing omega L into Im as V, or let me write omega L into Im and at an angle of 90 degrees, of course. So we should use, yeah, so I am using everything in peak value, so no issue. So this can be set as V at an angle of 90, where V is the RMS value, which is equal to omega L Im by root 2. Previously here also the current I is equal to Im by root 2. These are RMS values. Preferably I will keep every magnitude to be in RMS value. Now sketch this phasor diagram. So on the alpha and beta axis, that completes the inductor discussion. See, where is the current? Current is having 0 angle. So where we should place that? Current I am trying to place on the alpha axis, which is 0 reference, 0 degree. This is what the current magnitude. What about voltage? 90 degrees, plus 90. So from 0 you travel 90 degrees in anti-clockwise direction, which is positive angle direction. Thereby you reach to the beta axis. On the beta axis we will get 90 degrees. So on the beta axis, now let me put the voltage. This is what the voltage B. So whose angle is 90 degrees. See, magnitude is length. Angle is its alignment. Angle is its alignment. So this is what the phasor diagram of a inductor. Phasor diagram of a inductor. Phasor diagram. So we continue this discussion in the next class. Okay. Thank you.